Welcome to Chemistry with Caroline. In this video, we're going to look at intermolecular forces. Intermolecular forces are the attractive forces between neighboring molecules, and they can have a lot to do with the physical properties like melting point and boiling point of different types of molecules. So intermolecular forces can be grouped into three main categories, and we're going to take a look at the first one here. That's London forces, sometimes referred to as induced dipole interactions. So all molecules have London forces. It's just basically the movement of electrons to create a temporary dipole in a molecule. So if you think about pentane, it doesn't have any polar bonds, it's just carbons and hydrogens, but there's a kind of a cloud of electrons in that molecule. And what can happen is that a temporary dipole can form. So maybe on the right-hand side, there's more electron density, and on the left-hand side, there's less electron density. So this temporary dipole induces a dipole in the neighboring molecule. And so because this side right here is partial negative, this side becomes partial positive, and the electrons get pushed a little bit over to the right-hand side. So basically they're like little magnets, very, very weak magnets, lining up so that the oppositely charged ends of the molecule are near one another. So these forces are present in all molecules because all molecules have electrons involved in the connectivity of those atoms. The next intermolecular force we'll discuss is dipole-dipole interactions. So these are molecules that have a permanent dipole. So there's a polar bond in the molecule, a difference in electronegativity between two atoms that are bonded to one another. So in the case here, we have a fluorine and a carbon bonded to one another. Fluorine, of course, is very electronegative. It has a high affinity for electrons. So you'd have a partially negative fluorine and a partially positive carbon atom there. So there's a dipole moment, and it's facing this direction. And that dipole moment exists all the time. It's not induced. It's always there. So then what happens is that as the molecules are in close contact to one another, again, they're going to line up like magnets where opposites attract. So over here below, you've got another molecule, and it's lining up so that the partial negative end is next to the partial positive end of the neighboring molecule. So again, if I drew my dipole moment, it's facing towards the fluorine. This is the partial negative end of that molecule. It's lined up so that it's next to the partial positive carbon on the above molecule. The partially positive carbon that I'm noting right here is next to the partially negative fluorine above it. So these intermolecular forces are sort of medium strength or intermediate strength. They're stronger than the London forces, but they're not the strongest intermolecular force. And they are going to be present in all molecules that have a significant dipole moment. So basically, anytime there's a bond between a less electronegative and a more electronegative atom. And the bigger the difference in electronegativity, the stronger the dipole moment, and the more attraction between those molecules. The strongest intermolecular force is hydrogen bonding, and hydrogen bonding only occurs in molecules that have an HF, an HO, or an HN bond. I'm going to draw a depiction of two water molecules interacting with one another so you can see sort of what this looks like. So I'm going to draw two next door to one another. So because of the very polarized nature of these bonds, you get these attractive forces between a hydrogen on one water and the oxygen on the neighboring water. And we usually draw a little dashed line like this to indicate these interactions. So these dashed lines here indicate hydrogen bonding. Now, hydrogen bonding is only about 2 to 5% as strong as a true covalent bond, and yet it's responsible for holding our DNA together, and it's also a major component in determining secondary and tertiary structure in biomolecules like proteins. So this is the strongest intermolecular force that we've discussed. So you have London, then dipole-dipole, and lastly hydrogen bonding intermolecular forces. And again, you can only see hydrogen bonding interactions in molecules that contain HF, HO, or HN bonds. So to recap, we've got the strongest intermolecular force, hydrogen bonding. Intermediate strength intermolecular force is the dipole-dipole type interactions. And then the weakest intermolecular force that's present in all molecules is London forces. And we can see this if we look at two molecules that have a similar molecular mass, but very different properties. So here we've got water on the left, and then I'm going to draw methane on the right. So water has a mass of 18 grams per mole. Methane is 16 grams per mole. So mass-wise, they're pretty similar to one another. Water, we know, right, is a liquid, and it's got a boiling point of 100 degrees Celsius. At room temperature, methane is a gas, okay? They weigh almost the same. The difference is intermolecular forces. Methane has no dipole moments, so it doesn't have any dipole-dipole interactions. It can't hydrogen bond because it doesn't have an OH or an NH. You can see that water, however, has strong dipole interactions and also hydrogen bonding. So with a mass difference of 2 grams per mole, we go from a gas at room temperature to a liquid with a very high boiling point. And that is because of those strong intermolecular forces. You have to overcome those to vaporize water to get it to move from the liquid to the gaseous state. So this has been a look at intermolecular forces. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.